Hello, everybody, and welcome to the last week of class. Last week of class, second to last lecture. But actually, technically speaking, it is the last lecture because this last little bit of new material. Wednesday is just going to be, as a reminder, the final quiz, which will happen in class. 10 questions, all multiple choice. But you will get you can get partial credit for any work that you show. There'll be space provided on the quiz for you to work through the problems, and then the bottom of every question there'll be a multiple choice section where you can circle your answer, but it has to be taken in class. So please make sure you are arriving. For people who are not here, I'll send out an email tonight and probably an email tomorrow as well. But in the meantime, the last section. So section. Yes, go ahead.
The exam, the big exam,
Mhm.
that's also just online, right?
Yes, great question. So the last exam opened up this week. It opened up earlier this morning, and it will be due at I have it due at Friday at the moment, but I'm going to extend the due date until Sunday. Since we won't, like, normally we were covering all the material the week before, whereas today, like, we're going to be finishing up the material, so I want to give it a little extra time. So it'll be due Sunday of this week, and then yeah, but it is online. Same situation as always. 3 attempts, keep the best score. The only thing that doesn't have the 3 attempts is the final quiz. That has to be done because it's departmental. It has to have specific requirements, and one of those requirements is that it's a one-time assessment. So,
Just wanted to double check.
oh no, great question. So this one, section 4.5, is on expected value and fair price. So this is how you could draft up this idea of a game for your child to do in middle school and elementary school and high school to try and get them to get that side hustle and mess with other kids. I'm of course kidding. That's a terrible concept. But expected value. So, definition. The expected value, which we will now for now write as EV. Yes, expected value, EV. The expected value on a quote unquote game. And I put game in quotation marks because these aren't like, when I think of game, I think of something that, like, this is a game of chance, purely a game of chance. So all the things are going to be based on purely probability. On a game is the long average if the game was played numerous times. It is not the actual value of an attempt at the game, but rather what you will make / lose on each attempt. So it's not going to be like, when you think about the expected value, it's not going to be like, oh, this is how much I'm going to get win, or this is how much I'm going to lose, because it's a game of chance. Every single game You could win, you could lose. But if you were to play this game infinitely many times, then the expected value would be what you would be expected to win on average each time you play, or lose each time you play. So I remember when I moved out here, so I was living in Ohio, and we had just gotten, my wife and I had just gotten these jobs. And a person had asked us, like our neighbor had asked us, like where we were moving to and everything. And we said, we're going to Vegas. And it's like, oh, so you're going to be playing those slot machines, right? And like, you just need to play them enough and you'll win big, which is not the way it works. That's not how probability works.
They technically would get, like, they run up with zero.
Well, that's actually what this is. Expected value is what's going on. So they, like, in essence, yes, they are quote unquote rigged to the casino's benefit. So that only a handful will actually win. And I'm sure there's far more that goes into it because it's very, very technical nowadays. But at the core, it is trying to make sure that the expected value is negative. And so we're going to go through it, but the formula is this. EV, the expected value, is equal to probability number one times result number one plus ... plus last probability times last result. Let you write that down.
Oh, thanks.
So the ... means that it's going to be all the way up until you've reached the last probability. So if there are 6 different outcomes of the game, you'd have 6 different products. You have the first product, second product, third product, fourth product, and you add them together.
Is there a way to streamline that, or you just have to add every single one?
You have to add every single one, but the good news is a lot of the times they only have usually 1 to like 5 results.
Oh, good, so you're not adding like.
No. Like, God help us if that's the case. That'd be very, very tedious.
That would be.
Now, for if you could imagine, so we'll do one, and then I'll touch back on that with regards to casinos. So here's an example of a game that your child could play so that they can rig it in the theoretically. Well, actually, no, this one will be rigged so that your child wins. Theoretically. Just on the off chance. That they like, if they do this, then you can scold them, but then ask them for the money on the side. Suppose a game costs $5 to play, where you roll a D6. So a 6-sided die. Not a very, very exciting game, but it's a game of chance. So if you roll a 3 or below, you get nothing. If you roll a 4, you get $4. If you roll a 5, you get $8. And if you roll a 6, you get $16. What is the EV? What is the expected value of this game? Not a very exciting one, but I mean, think about like a slot machine. It's not like there is one aspect to the game. You just press a button and see if you win or lose.
Before very.
Oh man. My father-in-law is a pretty sizable gambler. And one of the first times I met him, he actually ended up winning $1,500. And just so he just gave us $100 to just try and play the slot machines, which is pretty fun. I always go into playing slot machines and stuff like that. I go into a casino with the intention that I'm going to lose the money. So I only go with $50 or something like that. Good. I will let them win. Like I'm basically, it is. I'm paying for a service. Like
You expect disappointment, then you can't be disappointed.
exactly right. I'm paying for the experience. That's what other way I like to think about it. But okay. So for this one, everyone has their own way of doing it, and if you can make this quicker, but I find that this is very, very streamlined and understandable. So what I like to do is I like to make a three-row chart. So we have outcome, we have probability, and we have result. So the outcomes are all the different possible endings to the game. Let's write that chart and then we'll go through it. So the outcomes, there are 4 of them. There is a 3 or lower, 3 or below, excuse me. There is rolling a 4, a 5, or a 6. So now we look at the situation and figure out the probability of those things. What's the probability of rolling a 3 or below? 3 out of 6, right? There are 3 ways that you can win, either rolling a 1, a 2, or a 3. Not win, but there are
technically
lose technically. So that's 3, 3, 2, and 1. So that's 3 different options out of the 6 total options. So a 3 out of 6 chance. Same then for rolling a 4, rolling a 5, or rolling a 6, that's only one of the options. So it's a 1 in 6 chance. Right? Now the result is what will happen at the end of it. So John Doe student says the result of getting a 3 below is 0. They're not wrong, but they kind of are. The result is, like, imagine you're playing this game. Yes, you win nothing, but it costs $5 to play the game. So there's a net loss of $5. So negative $5 here. And I've complained about it before, but why do we have to put the dollar symbol in front? Why?
it's just so distinguished cents and dollars.
But like,
It's one of those,
I always forget to draw it.
it's the negative, like, how do I put this? Like, negative what? Watermelons?
Yeah. But like, I want the symbol at the end because I always forget to draw it until like after I do it, and then I had to erase. If you roll a 4, you win $4, but it costs $5 to play, so you're out $1. So negative $1. If you roll a 5, you get $8, so you gained $3. And then last but not least, if you roll a 6, you win $16, but it costs $5 to enter. So you're going to get a net positive of 11. So we can even write that here. All of these, because it costs $5 to play. So now that we have the chart and the probabilities, all we need to do is just take the results and probabilities and multiply them together and add those things up. That's how expected value is calculated. So EV is going to equal 3/6 times -5 plus 1/6 times -1 plus 1/6 times 3 plus 1/6 times 11. And we're going to be rounding these things, by the way, to 2 decimal places because we're dealing with money. So we want to round to the nearest cent. So the EV is equal to that. And if you plug that into your calculator, you should get negative 0.33 repeating. So approximately negative $0.33. So roughly $0.33 every time you play will be lost. The player who plays. So the house, the person who is administering the game, they're expected to win 33 cents per game on average.
It's not bad, especially like 1,000 people playing. every
Yeah,
day.
if you do this in the playground, like with like 100 kids, that's like $33 if everyone plays once.
Theoretically.
Theoretically, it just like in this hypothetical world where you have a child who's willing to make a gambling ring in their
I don't know.
elementary school.
They'll probably put it into 10 or something like this.
But it's all theoretical.
That's true, they never did.
I know, and I mean, is there any rule in the? I mean, that's what I would do as a parent. Theoretically, is that if my student did that, if my child did it, it's like, is there a rule against making gambling games in the student handbook, like the student code of conduct?
Just say that they're playing pretend.
Exactly, it's play and pretend with real money.
Monopoly money, guys. Don't you know that?
So what this is saying, so our EV was negative. This means that if we were to play this game several times, each time we'd lose about 33 cents on average. Right? Sometimes we would win. If we played this game like 100 times, we'd probably be out about $33. If we played 100 times. And that's because like sometimes we might roll a 6 and get that $11. And then maybe we roll it again and we get another $11, but then we start rolling a 1, a 2, a 3 several times. And we start losing more and more money. So it's not saying that every time you play, you're going to lose 33 cents. It's saying that if you were to look at the, like how much money you have or have lost at the end of playing, on average, each game you were losing about this much. Does that make sense? So this is like expected value is from like, I mean, it depends on the situation you're looking at it, but like usually speaking, expected value is looking at the player's perspective, what the player is expected to win or lose. So back to casinos, they try to make this so that they like the expected value, like one of the things that they're trying to optimize is like that they're probably taking in a bunch of data to figure out how many times people are willing to lose before they are willing to give up, and trying to find that perfect cutoff point because gambling is an addiction, and trying to play off that situation. But like their games always have a negative expected value for the player, because if they have a positive expected value, then they'd be losing money on average. And it is a business, and you don't like a business where you're not making money is not very profitable. So that is the issue. Any questions on that expected value? Okay. Let's do several examples. Just so you encounter all the different situations that you might see in your homework and stuff. An example. A game costs $2 to play. Where you draw one card from a standard deck. If you draw a queen, you get $20. An ace, $10. A male face card, you get $5. An even card, $1. And an odd card, nothing. Find the EV. Whew. Well, that's all right. And then also with regards to casinos as well, like if you're talking about if you're talking about the expected value of their slot machines, so those ones, there's a bunch of different ways that you can win points or whatever. Like sometimes like it costs like 1,000 points for a spin, and you only get like 800 points back, just like this. So like if you draw an even card, you don't lose everything, but you lose about 50%. Like you lose 50% of what you put in. But they have computers to calculate these expected values, and it, as I said, it's probably not at like, I say probably because I am not a slot machine engineer. I don't work for the casinos, but I would assume that there's at the core expected value is being used, but they probably have a lot more statistical models that they use in the programming of those slot machines. So, solution. We're going to do another one. So we're going to write our little chart, outcome, probability, and results. So there are, in this case, there's 1, 2, 3, 4, 5 different outcomes. You could either draw queen. You could draw an ace. Male face card. You could draw an even. Or you could draw an odd. So, what is the probability of drawing a queen? Four out of 52, exactly right, because there is one queen in each suit, 4 suits, so there's 4 queens. So 4 out of the 52 possibilities. And we can like also how you fill in the chart is your prerogative. If you want to go outcome by outcome and fill in each column, that's okay. It's all what you'd like to do. So let's do it that way this time. So the result, you'd get $20, but it costs $2 to play. So that's a net of $18. And I'm not going to draw the dollar symbol anymore. It's dumb. An ace. Same situation. There's only 4 aces in a deck. It's one of each suit, so a 4 out of 52 chance. And you get $10, but you paid $2, so it's an 8 net. 8 net dollars, so 1. A male face card, there's 8. Yeah, 8 out of 52. Exactly right. Jacks and kings, there's 2 male face cards in each set, or in each suit, 4 suits, 8 total. So 8 out of 52. And that way you would win $5, but you paid $2, so $3 net.
Good.
No, but I mean,
Little goes along.
it's only $2 to play a game. So an even card. There is 2, 4, 6, 8, and 10. So there's 5 even cards in each suit. So 20 total. 20 out of 52. And when you draw an even card, you lose $1 because it costs $2 to play. You win $1, but you paid $2 to play, so you're out $1. And then last but not least, odds. So there's not 1, remember, because ace is 1, technically speaking. And that's not, so that's an ace, it's its own situation. So 3, 5, 7, and 9. So there's 4 odd cards in each suit. 4 suits, that means there's 16 situations where you'd lose $2. Now, one thing you should do, you're not required to do it, but it is a good way to check to make sure you're doing it right, is the numerators. If you add up all the numerators, you should get 52. Because you want to be able to cover, like, it should be the case that every single situation is covered. Like, every single situation should have a result. And so 4 plus 4 is 8, plus 8 is 16, plus 16 is 32, plus 20, that's 52. So we know we've got all the situations covered. The results, that's where we have to be, like, there's no really way to check that, but what we do know is we've covered all the probabilities. So the EV is just going to take all the results, multiply them by their probabilities, and call it good. So EV, 4 out of 52 times 18 plus 4 out of 52 times 8 plus 8 out of 52 times 3 plus 20 over 52 times -1 plus 16 over 52 times -2. There's a lot of symbols going on here. There's a lot of, when you're plugging, like, we're not going to do this in our head. That would be unnecessary. So we use our calculators for these things. So just take your time entering it, because there's a lot of divisions and pluses and so on and so forth, and negative signs. So always just take your time with it. Mhm.
When you say, like, multiply this, would you multiply each fraction by itself and then the other numbers by themselves? And then would you multiply?
Sorry, say that again.
Would you multiply each fraction by the fractions separately?
By each fraction.
Like, would you multiply the fractions separately and then the amounts separately?
I see. I would recommend just trying to plug the whole thing into your calculator at the same time. But you can all, like, if you wanted to calculate it in a different way, I would recommend, like, if you don't want to plug the whole thing in at the same time, calculate each little sub chunk separately and then add those together.
I was just curious, like, how would you build that?
Yes, I would just try to plug in the entire thing, but
Keep that,
each record.
and then add.
Yes.
Got it.
And I would probably recommend, if that's the case, if you need to calculate each one separately, that you write down probably 3 or 4 decimal places for each one. That way, when you're rounding, you don't, like, double round, quote unquote. So if you plug this into your calculator, approximately you will get $1.46. $1.46. Meaning that if you play this game, your expected value, if you play this game 100 times, each time you're going to win about $1.46.
Oh,
Not bad. So I got some bonus questions. This is kind of leading, like this is kind of doing our little bit of bring it all together. Bonus Q. It's a bonus, which means it's fun. If you played this game 125 times, what could you expect to for a payout? What will you expect for a payout? So remember, this is a game completely of chance. It's a game completely based on chance. So there's no skill needed here. It's just purely chance. Whereas like with not with blackjack, but with poker of any sort, there is an element of skill involved. It's a lot of chance, but there's also a lot of skill in reading your opponent, seeing what like their play style, when they call, when they like all their tells or whatever. So this one, in case you don't know, and it's not that hard of one to calculate, but just by doing it with your calculator and not even using this aspect, but this is a unit conversion, right? 125 games times, for every one game, there's an expected payout of $1.46. The games cancel, and boom, you just have dollars. So, where's my calculator? $1.46 times 125 is $182.05. Not bad, not bad. If you played it 125 times, that's a tall order, but oh, it would. And this is not to say, like, remember, this is all based on chance. So this is based on the probabilities provided. You could end up making way more. It could be that every single time you play, you draw a queen, in which case you'd make a lot more money because each time you'd be gaining $18. 18 times 125 is $2,250. So like you could win up to that much, or you could lose up to $250. But on average, a person playing at $125 would make about $182.50. So this is an expected amount that you'd get, not necessarily guaranteed. You might make a little more, might make a little less. And so then follow up to this question to do another unit conversion to help us practice for the final quiz. Suppose you can play this game every 21 seconds. Like you play it, you get the result, they give you the cash immediately, like, or it's virtual, so they can give it to you, and then you put in your card again, just swipe to play it again after 21 seconds. So you can play it every 21 seconds. Then the question is, what would your hourly wage be? You know that fun thing, it's like a crank, and you can like, it's literally free to do. You can crank it, and for like it's supposed to represent how much physical labor you'd have to do for minimum wage. Like, so you sit there and crank it, and after you stop cranking, like it's designed, like I can't remember exactly the payout, but they'll give you like 25 cents every 15 seconds you're cranking it, or how like every time. So like it shows you how hard you'd have to work for the low minimum wage in places like Ohio of like $8 or whatever it is. Maybe it's changed since when I last looked. I would hope so. I would hope so. Some places have gotten with the times, but whatever.
How you move.
To be fair, the cost of living there is a lot lower. Like say what?
Still,
But I mean, still, you can see why it's low.
Yeah. I mean, I remember like when we were there, we were considering settling down there, and like the average house price was in like the $150,000 range. So, but then that was in like 2014 or so, like that, like when we were looking. So, and things went bonkers after COVID. Like
yeah.
people selling their house for like twice of what it's worth. So either way, it's probably a lot higher now, but it was very, very reasonable at the time. Once again, this is a unit conversion. We know that you earn $1.46 for every game. And you know that every game, one game can be played every 21 seconds. One game per 21 seconds. And so the games cancel. And so now we have dollars per second, but we want an hourly wage. So we want dollars per hour. So we got to keep going. We got to convert those seconds into hours. So you can either use the unit conversion that there are 3,600 seconds in an hour, or you can convert to minutes and then convert to hours, which is the way I would do it because I don't want to memorize that fact. So 60 seconds to 1 minute, and the seconds cancel. And then 60 minutes for every 1 hour, and the minutes will cancel then. And so now we have, if you look at the numerator, the only measurement we have is dollars, and the denominator, the only measurement we have left is hours. So we have our dollars per hour or our hourly wage. And if you plug that in your calculus, that's going to be 1.4, oh, one color. 1.46. So I want to make sure that I was recording. 1.46 times 60 divided by 21, right? Because it's 1 times 21 times 1 times 1. The ones don't matter. And if you plug that into your calculator, you get an average, an hourly salary of $250.29. That would be your hourly wage. Not bad, not bad. And so that's actually, that's not bad at all. If only. If only. Right. One of my colleagues, he was actually a professional poker player as well. And he made more money from poker playing than he did from teaching here. Which sends the message, get out of school. Not worth it. Just gamble.
You're pretty good at gamble.
True. Which is why you shouldn't quit school. It's awesome. So I'm, of course, I'm kidding with that statement. But anyways, so, and once again, though, this isn't a fabricated game where the odds are in your favor, which they never will. They never will be. Not in any game of gambling that you see around. Any questions on that? So unit conversions, one of the most, I like kind of wrapping up the class a little bit. They are probably the most important thing that I want you to take away from this class, because you can use unit conversions everywhere. Everything in your life, not everything, so it's a blanket statement, but a lot of things in your life can be simpler if you know how to do unit conversions. How much is it going to cost to remodel your floor? If you can find out your square footage and the cost per foot of material, you can get a rough estimate and then plus or minus labor.
Labor's
True, unless you want to make a 2-day project into a 2-year project and do it yourself. Say, oh, I'll do it, honey, I'll do it, I promise.
So,
I've been telling my wife that I will trim one of the trees in our house for 2 months.
2 months.
2 months at this point.
Is it a
Right.
big tree or?
What it's going to require a ladder, but that's about it.
Then get a gardener.
I could, but
For yourself.
that's money, and that's money that I could spend on buying Pokemon sweaters. So,
Priorities.
I do have my priorities in the right spot. Not saving money for my son. That's not important. Pokemon sweaters over everything. A game is that's what I want to remember him by. How many Pokemon sweaters I give to him at the end.
Son, you didn't even go to college.
Maybe they'll be worth something.
Maybe.
All time back to chances.
Anyways, sorry to get sidetracked. A game is played by spinning the following wheel once. What is the EV? So you have your circle. And then there's a line straight down the middle. And then, oh yeah, that's totally where I wanted it. And last but not least, there's this little slice. And so they don't tell you how much the game costs. They just tell you what you're going to win or lose. So they take care of the fact that this situation, they already tell you what's going to happen. You don't have, there's no paying for the game. It's just, if you play it and you lose, you have to just give them the money. So in this square here, you lose $4. There's a 25% chance because it's a quarter of the circle. In this bottom quarter circle, you win $8. That's also a 25% chance. In this slightly larger portion, the bottom left, you lose $3. And that's a 37.5% chance of losing. And last but not least, you win in this tiny sliver, you win $10. That's 12.
Not in your favor.
No. But the payout's pretty good. That's what it is. Now notice this doesn't give you probabilities. It does, but it doesn't. We're used to seeing probabilities as fractions, like a 1 in 2 chance, or 1 in 8, or 1 in 6, or 4 out of 52, and things like that. These are giving it to you as raw percentages, because the odds of flipping a heads on a coin toss, it's a 1 in 2 chance, but you could also think of it as a 50% chance, because 1 divided by 2 is 0.5. So this is just giving you the raw percentages of the probabilities. So the probability of losing $4 is 0.25. The probability of winning $8 is 0.25. The probability of winning $10 is 0.125, and so on and so forth. So the EV for here, solution, the expected value is equal to 0.25 times -4, because you're going to lose $4 in that first quadrant, that first top right, plus 0.25 times +8. And once again, we don't need to worry about the whether or not you need to take into account the cost of the game, because there is no cost. It's just assumed that if you do spin on a losing spot, you will give the person the money. Plus 0.375 times -3 plus 0.125 times 10. And if you plug that into your calculator, you should get 1.125, which will round up to $1.13. So the game is in your favor. You should play this game bunch because hypothetically speaking, each time you play, you will win some money. Hypothetically speaking. Any questions on that?
Percentages are just taken from like.
Yes, from 100%. And so 0.25 plus 0.25 plus 0.375 plus 0.125, that'll add up to 1.00 or 100%. All right, let's see here. All right. A couple more, and then we'll talk about fair price. Example, CSN has a raffle that costs $2 to enter. First prize gets $1,000. Second prize gets $500. And third and fourth prize gets $100. Not to share, each person gets $100. Third and fourth place, those ones. Find the EV if tickets get replaced each time and 5,000 tickets are purchased. So that replaced each time comes in handy because imagine they draw a name out of it and then that significantly changes the odds because now there's one less person unless they do it. So this is so in this situation, it is possible for the same person to get drawn for first, second, third, and fourth prize. Highly unlikely, right? That's a 1 over 5,000 to the fourth power. That's a very, very unlikely situation for that to occur, but it could happen because each time the amount gets replaced. So solution. We'll write our chart, outcome, probability, and results. And so the probability of the outcomes are either first, second, third, and fourth is its own outcome, and then everything else. So you could either win first place. Let's just fill them in as we go along. What is the probability of winning first place? 1 out of 5,000, because there's one way for you to win is if your ticket gets drawn, and there's 5,000 tickets total. So a 1 in 5,000 chance. And if that's the case, since it costs $2 to play and you win $1,000, you net 998. You could get second prize, which would be also a 1 in 5,000 chance. And that would give you a payout of 500, so you get $498. You could get third or fourth. Now you could treat these as two separate entries if you wanted to, where there's a 1 in 500 chance of getting third place, and there's a 1 in 5 chance of getting second place, or sorry, 1 in 5,000 chance of getting third, 1 in 5,000 chance of getting fourth. But we can also just combine them and say there's a 2 in 5,000 chance of getting third or fourth. And then that's going to be a payout of $100, but that's going to be $98 net, or you could lose. Only 4 people are picked to win. So the other 4,996 people, which is 5,000 minus 4, those people lose. 4,996 out of 5,000, you lose $2, so minus 2. So we've got our chart. All we need to do is multiply the probabilities by the results, add them together, and we've got our answer. So EV will equal 1 over 5,000 times 998 plus 1 over 5,000 times 498 plus 2 over 5,000 times 98 plus 4,996 over 5,000 times -2. And if we plug that into your calculator, however you want to do it, you end up getting approximately -$1.66. I always forget to put the dollar symbol. So as a small follow-up question, just as a critical thinking question, how much money does CSN make from this raffle?
First,
Mm-hmm.
and there's 5,000 tickets, when that's the
10,000, but then remember they have to pay the people.
So then, where the
So 1,000, 500, and 200. So $1,700 has to get given off.
so 8,000.
Yep, exactly. So so with this raffle, CSN would make $8,300. Not bad. Not bad.
Money.
Yeah, rent for 1 month. Am I right, guys? Rent is too damn high. If anybody remembers those memes from the old days. Everyone remember those memes? Standard things like socially awkward penguin. That was a good time. It was a good time of the internet.
So like, was that alongside like the critical thinking after?
Oh yeah. Velociraptor. Yes, all that stuff. That's the golden age of memehood. Memehood, yes. All words are made up. But okay. Getting sidetracked. Last subsection of this one, but then there's also like kind of things that we can do based on this. So fair price. Up until now, I've always been giving you the game. But one of the things that gets asked with altruistic memes is, how can I make sure that this game is fair? It's not rigged towards me or rigged towards the other player. The definition: the fair price to play a game is the price point at which the EV, the expected value, equals 0. Because if the expected value is 0, well, I'll let you write that down. Talk about it. Because in order to be fair, it means that there's an equal chance of winning and losing. And in terms of expected value, that would mean that it would have to be 0, meaning that each time you play, if you were to play 1,000,000 times, you'd expect that you wouldn't win anything or you wouldn't lose anything on average, right? Based on probability, it would be expected that after playing the game, you don't end up winning or losing anything. That's what it would mean for it to be a fair game, where nobody is expected to win or lose. So, as an example, how to use this. A carnival game has a basket with 4 envelopes. Comma, in which a player picks one envelope. The envelopes contain envelope looks like a weird word now. All right. I guess, is it envelope or envelope? Screw the English language.
It's like the difference between saying caramel and caramel.
Yes. Or Caribbean or Caribbean.
It really just depends on where you come from and what the dialect is. I hear people say it both ways. I always heard envelope.
Envelope. It sounds more proper to say envelope.
But then my mom says you pronounce it envelope. She's an English teacher.
Oh, okay. Well, if she's an English teacher, then I'll trust her. So envelopes contain $1, $10, $20, and $50.
Also, you missed the end of the first envelope.
Envelopes.
Where?
Envelopes.
Four envelopes.
And there we go. Oh, whoa, whoa. There we go.
There you go.
All right. What would be a fair price? So notice that the cost of the game was not mentioned. So when we're creating our results here, we're assuming that the game is going to cost $0, so that we can figure out how much that we should charge in order to make it a fair game. Does that make sense? So we're going to do this. We're going to calculate the expected value as if you could just play this game for free. That would give us the expected payout if you were to play the game. And then from there, we figure out how much they should charge, if that makes sense. So the fair price for solution . The fair price will be determined by finding the EV if there was no buy-in, if there was no cost for playing. once we see it, like it'll be useful to see the numbers first to explain why this is the process, but we'll get to that. So we have the outcomes, probabilities, and results. We'll make a new chart. Granted, if you want to skip the chart, if you're able to keep it all in your head and make sure that everything goes according to plan, you can skip this whole chart that I make, but it's never a bad thing to do that. So outcomes, probability, and then the results. So the outcomes, you can draw one of 4 envelopes. So we'll just call them 1 through 4. And since there's nothing here saying like one envelope gets picked more often than the other, we're assuming that they all have an equal chance. Like the person just gets a 1 in 4 chance, right? 1 in 4 chance they pick up envelope 1, 1 in 4 chance they get envelope 2, and so on and so forth. So envelope 1, envelope 2, envelope 3, and envelope 4. All of them have a 1/4 chance of being drawn. And so we're going into this, we're calculating the expected value if it didn't cost anything to play the game. So if that was the case, if it didn't cost anything to play the game, if you drew envelope 1, you'd win $1. Envelope 2, you win $10. Envelope 3, you'd win $20. And envelope 4, you'd win $50. Though I've just assumed that envelope 4 is the one that has $50 in it, but like however you want to arrange it is fine. You could say that envelope 1 has 50, then 20, then 10, then 1. It doesn't matter, because they all can be drawn with the same probability. So the expected value is going to be 1/4 times 1 plus 1/4 times 10 plus 1/4 times 20 plus 1/4 times 50. Since they're all being multiplied by 1/4, you could factor that out front and just add the 3 and the 4 numbers for price totals, but that's using algebra that we don't need. You could still just plug this into your calculator and you will get that is 2025. That is the expected like the expected payout if you were to play this game with $0 required. So that would mean that the fair price is that amount. Fair price is $20.25. And if you want to, I recommend going back and checking, like make it so that the game costs $20.25 and then redo the chart. So that would mean that the result 1, like 1/4 probability is still the same, but then your result will be negative 19.75. No, 0.25, excuse me, 19.25 and so on and so forth. And then $10, so 10.25 negative, whatever, what you get what I mean. And I guarantee you, if you do that, you will get the expected value of the game. Once you make it cost $20.25, you will get an expected value of 0. So the reason why this, just to recap why this is the way we calculate fair price, is if you find out what the expected payout will be if it doesn't cost anything, that would give you how much each person would be expected to win each time they play the game. So if you want to make the game fair, meaning that nobody wins, nobody loses, you need to make the cost of the game that, so that nobody wins and nobody loses. Hypothetically, if you were to play the game over and over again. Because of course, if you play it once, you're going to get one of those 4 outcomes. But any questions on that? Alrighty. Okay. Example. We got two more examples. That one is harder because there's more than just chance involved. There like it all like there are so many variables involved, right? Because like how you grab the claw, like how you grab the prize will change the outcome of it grabbing it. And plus some of them are rigged so that the claw doesn't hold it very hard. But that's a tough one. I don't know how they calculate that. Or like how they decide to like they probably just try and make it as flimsy as possible. But yeah, off the top of my head, like there would be a lot going on to figure out the expected value there. Sadly, not something we could calculate. But
Well, there is a place called The Claw in Vegas.
Really?
Heard of it?
no, I would not.
It's like, well, you just go and there's a bunch of claw machines.
Oh, really?
And so you get to play a little bit more and you kind of get to like test the chances. So it's kind of cool.
And so on that front, then we can also talk about what would be called empirical probability. If you remember in the very, very beginning in 4.2, we talked about there's theoretical probability, which is what should happen based on math, versus what is empirical probability, which is taking a bunch of attempts at the game to finally figure out what the probability should be. So if you play it 16 times and you win twice, then you have a 1 in 8 chance of winning. So, but yeah, I haven't heard of that. That'd be a very fun thing to do. Should put that on my list of things to do. A school wants to have a raffle with a prize of $200. A prize of a $200 gift card to Culver's. Culver's, does anybody know what Culver's is? So it's a fast food chain that only happens in the Midwest. It's like, have you ever been to Freddy's? Freddy's or Steak and Shake, very, very similar. But let's not write Culver's, that's stupid. Let's go with something far more applicable. Dave and Buster's. Good old D&B. You can write whatever you want here. If you want it to be Outback Steakhouse or something like that, who cares? The school intends for this event to be fair. Meaning that we want a fair price. That's what that means. If they say that they want the event to be fair, it means they want the expected value to be 0. If there are 1,500 students, what price should be charged? So we could make a chart for this one, but there's only 2 outcomes. Either you win the raffle or you lose the raffle. We're going to go into it assuming that it's free to enter the raffle to figure out the expected value if there was no cost, and that number will be our fair price. So there's only 2 outcomes. You either win or you lose, and there's only 1 winner. So the EV, you don't even have to make the chart. And in all the other situations, you don't necessarily need to make the chart, but it is helpful, at least for me, to jot down my thoughts. So for this one, the EV, there is a 1 in 1,500 chance that you win $200. And in every other situation, you would lose. So in 1,499 ways out of 1,500, you wouldn't get anything. So that's 200 divided by 1500, which is 0.133 repeating. Excuse me, 0.133 repeating. So approximately 13 cents per ticket. To make the game fair. If they charge 13 cents per ticket, then the expected value would become 0, making the game a fair game. So this school is trying to just make sure that the game is fair to its students. How nice. All right. Okay. I got one extra problem that's like you don't. I'm pretty sure you don't see it on your homework or on any quiz or anything like that. But I thought it was a fun game, fun question that involves a little bit of algebra. So, last example, and then we'll call it a day. A game is played by drawing a single card from a standard deck. If you draw a face card, you lose or you win $20. Otherwise, you lose. How much should the game charge for losing if the game is intended to be fair? There's a lot of ways I could write this problem. Based on my verbiage, it's going to be a little bit challenging to understand because I haven't said that there's any cost to the game. Like there's no entry to play, but I could have easily done that. But what I've got here is solution. The thing is, this is a situation where we have an unknown. We want to know how much the game should charge you for losing. So we make that our variable. Let X equal the money you have to pay if you lose. So then we have outcome, probability, and results. Outcomes. There's two different situations. You either win or you lose. And you win by drawing a face card. Or you could lose. The probability of drawing a face card. There are 3 face cards in each suit, 4 suits, which means there are 12 different face cards. So there's a 12 in 52 chance of winning. And if you win $20. There's no price to the game. This is a game where you enter And you either have to get like you either have to you get paid or you have to pay them if you lose. And so every other way, so every other card, you could either count the amount of cards that would be, or you could just take 52 minus 12 to get you 40 out of 52. And in that case, you're going to lose X dollars. We don't know what X is, so we're going to find out. We know the expected value is going to equal 12 out of 52 times 20 plus 40 divided by 52 times X. And we want the game to be fair, which means we want the expected value to be 0. Because we want a fair game. So that will give us a linear equation, which we've had to solve before. Giving us a little bit of practice for the upcoming exam. Anything with that? So 12 times 20, 12 over 52 times 20, that is 240 over 52 plus 40x over 52. And there's a lot of ways we can solve this. My recommendation, remember, we want to get the x by itself. So honestly, what I'm going to do, instead of writing it like that, I'm just going to keep it as 40 over 52x. So we subtract 240 over 52 from both sides. To cancel it on the right, you get negative 240 over 52 equals 40 over 52x. And then we want to get the x by itself. So the x is being multiplied by 40 over 52. So in order to undo that, we would divide by 40 over 52. It doesn't matter how, like if you're going to do this in your calculator, make the numerator, make the first fraction in the big numerator, make that in parentheses, and then divide that by the other one in parentheses. So if you want to enter this into your calculator, please write it as this. Parentheses negative 240 divided by 52, end parentheses, divided by parentheses 40 divided by 52. Please put it in your calculator that way. Otherwise, it will not read it right. If you don't put the parentheses by it, it won't read it right. And if you do that, you get that x should equal 6, negative 6. So the game should make you lose $6 if they want the game to be fair. X has to equal 6. But I'm pretty sure there's no problem on your homework or anything that does this. So I wouldn't worry about this situation too much. I just thought it was a cute problem to involve linear equations. That will do it for today. So please remember, Wednesday, we have our final quiz that is due, that is taken in class. So you need to be here to take it. If you don't come to class that day, it is a 0. I'll send out an email today and tomorrow as a reminder, but it has to be taken in class. It is multiple choice, but you can get partial credit for correct work up until the answer. And it's going to be multiple choice, so you can circle the answers that you want. So I'll make sure there's enough space provided to work on each problem. And yeah. No notes are allowed because it's a departmental thing. Yeah. Nope. So once you take the quiz, you are free to leave. You're all set for the semester. Once you've taken that quiz on Wednesday, the course is over. So this is our last lecture. This is our last time we'll be talking at you, besides just telling you the directions. So since it is our last time, I just want to thank you for a great class, guys. I hope I'll see you guys on Wednesday, but I hope the rest of your classes are going well in terms of preparing for your finals. Okay, guys?
Okay.
I will see you guys on Wednesday.